Hello everyone. Today we'll be glossing over Lebesgue's integrability criterion because I am using the term glossing over because we'll be quite skipping over the details. So we'll just refer the book Introduction to Real Analysis from Bartle and Sherbet for the proof. So let me just highlight the criterion. Uh, it states that a bounded function f from a closed interval a to b defined from a to b to the set of real numbers is Riemann integrable if and only if it is continuous almost everywhere on the closed interval a comma b. So in other words, it has to be continuous. Um, it has to be continuous on the entire interval except some countable number of points. So, or the set of points where the function is discontinuous is a null set. A null set is not the same null set that you refer from the set theory. Here, the definition of null set is somewhat different. But I will not be introducing the notion of null set over here. So we'll just pursue the proof as we go along, a priori assuming that we know what a null set is and defined in the context of Lebesgue's integrability criterion. So so I'll be I'll be okay. So I'll be just okay. Sorry. I'm really sorry. I'll be just proving the implication part towards the right hand side. That is, if given if you are given that the function is continuous, then the set of as a function is Riemann integrable on that closed bounded interval, then we just have to show that it is continuous almost everywhere on the closed bounded interval. So epsilon is for any given epsilon is arbitrary uh, for each k belongs to n. Let h of k be defined as x belonging to the closed interval ab such that the oscillation of fn, I'm supposing that you guys know what oscillation of a point oscillation at a point is, or oscillation defined on an interval is. It's a very trivial definition. You could go through the standard textbook to capture the idea of what is an oscillation. Uh, we will show that we will eventually show that this function will show that h of k is contained in the union of a finite number of intervals having total length less than epsilon by 2k. So this will eventually show that h of k would be a null set, which we intend to prove. So before diving into the proof, I just want to make sure that the notation that is adopted in Bartle and Sherbet is somewhat ambiguous. So I will stop refraining from using those kind of notations. Especially over here, I will just highlight. So I will just be pursuing the proof in Bartle statement from now on, and I will just highlight the changes where the changes should where the changes would be needed, or where we need to embed things to make it a better proof, or to remove the ambiguities. So by the Riemann criterion, there is a partition. This partition is defined. Okay, so the notation of this is quite ambiguous, because we ended. These are, especially this should be denoted by xi minus 1 k x I comma k.